Hello everyone. So today we will see how to evaluate infinity by infinity form in this lecture. So, rules to evaluate limit x tends to a f of x upon g of x in the form infinity by infinity. So, rule number 1 is we have to check whether the limit is an indeterminate form or not. Because if it is not, then L'Hospital's rule cannot be applied. Rule number 2, here always differentiate f of x and g of x separately. That is, we have to differentiate numerator and denominator separately till we get finite values. We have to note that we don't have to apply division rule in the numerator and denominator, but we have to differentiate them separately. So now we will see different examples of infinity by infinity form. So our example 1 is evaluate limit x tends to infinity 3x square plus 8x plus 4 upon 4x square plus 5x plus 6 is given. Now if we substitute this limit in this equation, then we get 3 infinity plus 8 into infinity, that is, here we get infinity by infinity form. So we further differentiate this equation. So we get differentiation of 3x square is 6x plus 8x is 8 and differentiation of 4 is 0. Similarly, in the denominator we get 8x plus 5 plus 0. Again, if we substitute this limit in this equation, then we again get infinity by infinity form, because infinity into infinity plus anything is infinity. Similarly here, so we get infinity by infinity form. So we again differentiate above equation, then we get 6 plus differentiation of 8 is 0, and again similarly here differentiation of 8x is 8 plus 0, that is, we get finite value 6 by 8, that is 3 by 4. So 3 by 4 is our answer. Example 2. Evaluate limit x tends to 0 log sin x upon log tan x. Now again, if we substitute this limit in this equation, then we get log 0 upon log 0, because sin 0 is 0 and tan 0 is 0, and log 0 is infinity, so we again get infinity by infinity form. So we will further differentiate this equation. So we get log sin x is 1 upon sin x, and differentiation of sin x is cos x. Similarly, in denominator, log tan x is 1 upon tan x, and differentiation of tan x is sec square x. And this tan x will go up, so we will get tan x into cos x upon sin x into sec square x. Now, this tan x can also be written as sin x upon cos x into cos x will remain as it is in the denominator, sin x, and the sec square x can be written as 1 upon cos square x. This cos x and this cos x gets cancelled. So we get, again this cos square x will go up, so we get sin x into cos square x upon sin x. Again this sin x and sin x gets cancelled, so we get cos square x. And if we substitute this limit in cos square x, then cos square 0 cos 0 is 1. So we get finite value and 1 is the answer. Example 3. Evaluate limit x tends to 0 log sin x upon cot x. So first of all, we will substitute this limit in this equation. So we get log of sin 0 is 0 and upon cot 0. Value of log 0 is infinity and cot 0 is also infinity. So we get infinity by infinity form. So now we will differentiate this equation further. So first, if we differentiate numerator part, we get differentiation of log sin x is 1 upon sin x. And again, differentiation of sin x is cos x. Upon differentiating denominator part, we get cot x. So differentiation of cot x is minus cos x square x. So we can rewrite this equation as cos x upon sin x into minus cos x square x. But we know that cos x is equal to 1 upon sin. So we can write limit x tends to 0 cos x upon sin x, and in place of cos x square x we can write 1 upon sin square x, and this sin x gets cancelled, so we can rewrite it as this sin x will go up, so we get cos x into sin x. Now if we substitute this limit here, then we get cos 0 into sin 0. Cos 0 is 1 and sin 0 is 0. So we get 0. So answer of this question is 0. Example 4. Evaluate limit x tends to 0 log x upon cot x. So now again if we substitute this limit in this equation, then we get log 0 upon cot 0. That is again infinity by infinity form. So we get indeterminate form. So we will apply L'Hospital's rule. So differentiating numerator and denominator, we get limit x tends to 0. Differentiation of log x is 1 upon x upon differentiation of cot x is minus cos x square x. But we know that cos x is equal to 1 upon sin. So we can rewrite this equation as limit x tends to 0 1 upon x upon minus 1 upon sin square x. The sin square x will go up, so we can rewrite this equation as limit x tends to 0 sin square minus sin square x upon x. Now if we substitute this limit in this equation, then we get sin 0 upon 0. That is sin 0 is 0, so we get 0 by 0 form. So we again differentiate this equation further. So we get limit x tends to 0 sin square x. Differentiation of sin square x is 2 sin x, and differentiation of sin x is cos x. So minus 2 sin x into cos x, and differentiation of x is 1. Now again if we substitute this limit in this equation, then we get 2 sin of 0 into cos of 0, but sin of 0 is 0, so we again get 0 upon 1. That is, if we substitute this limit, we get 2 sin of 0 into cos of 0 upon 1. Sin of 0 is 0, so we get 0 upon 1, that is, so our answer is 0. So we get finite value as 0. So answer of this question is 0. Example 5. Evaluate limit x tends to infinity 1 square plus 2 square up to x square is given upon x cube. So to solve this equation, you should know the formula of standard series. So first of all, write down 3 formulas of standard series. Whenever 1 square plus 2 square plus up to x square is given, then its formula is x into x plus 1 upon into 2x plus 1 upon 6. So here we will apply this formula. So whenever x square term is given, then its formula is this. Now whenever it is given 1 plus 2 plus up to x or up to n, anything, then its formula is x into x plus 1 upon 2. And whenever it is given 1 cube plus 2 cube plus up to n cube or x cube, then its formula is x into x plus 1 upon 2 and whole square. But here we will apply this formula because the question is in up to x square terms. So limit x tends to infinity x into x plus 1. You have to directly write this formula of this equation here and then further solve. 6x cube will remain as it is in the denominator part. Now if we substitute this limit in this equation, then we get infinity by infinity form. We get infinity by infinity form. So we will further differentiate this equation, but we can rewrite this equation as multiplying x inside, we get x square plus x into 2x plus 1 upon 6x cube. So we will again multiply this both the brackets. So we get 2x cube plus x square plus 2x square plus x upon 6x cube. Now we will differentiate this numerator and denominator part because this is infinity by infinity form. So limit x tends to 0. Differentiation of 2x cube is 6x square plus 2x plus 4x plus differentiation of x is 1 upon 18x square. Sorry, here limit is infinity. Now again if we substitute this limit, we get infinity by infinity form. We get infinite in numerator part as well as in denominator part. So we will again differentiate this equation further. So we get 12x plus 2 plus 4 upon 36x. Again if we substitute this value, this limit in this equation, then we get infinity by infinity form because infinity plus anything is infinity upon infinity. So we will further differentiate this equation. So we get differentiation of 12x is 12 plus this will be 0 and differentiation of 36x is 36. So we get 12 upon 36, that is 1 upon 3. So we get finite value. So 1 upon 3 is the answer of this question. So our next example is evaluate limit x tends to infinity x raised to n upon e raised to x. So first of all, we will check whether it is in the indeterminate form or not. So for that, we will substitute this limit in this equation. So here we get, if we substitute this limit in this equation, then we get infinity by infinity form. So we can say that this equation is in the indeterminate form and we can apply L'Hospital's rule here. So for that, we will differentiate numerator and denominator. So differentiating numerator and denominator, we get limit x tends to infinity. Differentiation of x raised to n is n x raised to n minus 1. And differentiation of e raised to x is e raised to x. Now, if we again substitute this limit in this equation, then we again get infinity by infinity form. So, we will again differentiate numerator and denominator separately according to L'Hospital's rule. So, limit x tends to infinity is equal to n into n minus 1 upon x raised to n minus 1 minus 1 upon e raised to x. So we can rewrite this equation as limit x tends to infinity n minus 1 x raised to n minus 2 upon e raised to x. Now again, if we substitute this limit in this equation, then we again get infinity by infinity form. So we will again differentiate numerator and denominator separately. So limit x tends to infinity n minus 1, n minus 2 and x raised to n minus 2 minus 1, that is n minus 3 upon e raised to x. Now again, if we substitute this limit in this equation, then again we get infinity by infinity form. So now we will again differentiate this equation. So we get limit x tends to infinity n minus 1, n minus 2, x raised to n minus 4, n minus 3 upon e raised to x. Again we get infinity by infinity form, but this process will keep on going. So we can write this numerator part as n factorial. So limit x tends to infinity n factorial upon e raised to x. N factorial means it will go up to some constant term at last. It will end till constant term, end by a constant term. So now again, if we substitute this limit in this equation, then we again get infinity by infinity form. So we will again differentiate this equation, but n factorial means it will go up to some constant term and differentiation of constant term is 0. So our answer is 0. So answer of this question is 0. So next example, limit x tends to infinity log x upon x raised to n is given. So first of all, we will substitute this limit in this equation. So we get log infinity upon infinity raised to n. Log infinity is infinity. and here is in denominator part also we get infinity, so this is infinity by infinity form. So according to L'Hospital rule, we will differentiate numerator part and denominator part. So limit x tends to infinity, differentiation of log x is 1 upon x, and differentiation of x raised to n is n x raised to n minus 1. So we can rewrite this equation as limit x tends to infinity 1 upon x into n x raised to n minus 1. So now if we substitute this limit in this equation, then we get 1 upon infinity n into infinity raised to n minus 1. Anything into infinity is always infinity. So we get 1 upon infinity. And anything upon infinity is always 0. So answer of this question is 0. Now these are some examples of type 2 for practicing. There are 4 sums, and also the answers are given in the bracket so that you can verify whether you got the correct answer or not. So do practice this sum. Thank you everyone. I hope you all liked my video lecture.